Good day to everyone. So in the last class, we have seen about the relation between the different moduli, and we have derived the equations of the relation between the three modules and with the relation with the Poisson ratio. So in this class, we are going to see about the relation between the stress and strain in the form of how, suppose if I have an elastic material and I'm going to apply a load on the progressive load on it, and how this load is actually affecting this elastic behavior of the corresponding material. And we are going to do the next, we are going to do the another the simple experiment. That means we are going to derive the Poisson ratio of the rubber with the simple experiment. Okay. First, we are going to see the behavior of a elastic material under progressive stress. Suppose if I am going to take any elastic material, maybe the material which is made up of some, we take a wire which is made up of some material. So I am going to fix the one end of the material on the ceiling, and I am going to have a wire. Okay. So and there is a load is applying on this the other end. Okay, I'm going to apply a weight on the other end, and I'm going to measuring the stress as well as the measuring the stress in the form of adding the weight and the increase in the length in the, that is the strain. This is the stress. That means I'm going to adding the weight in the that is actually the manipulating the stress, and the length in the elongation of the length can be measured in the form of strain, and I'm going to plot the relation between the stress and strain. Okay, so I'm going to take this so this is the x-axis. I'm going to take stress, and then y-axis I'm going to take a strain. So stress is in the form of a load which I'm adding, and the strain is in the form of the elongation of the wire. Okay, so initially this wire is having the length of L, and I'm going to add some more weight on it, so that suppose if I keep on adding the weight, this length is actually elongating. So the so for the zeroth weight, I'm going to have a 0, means the strain is 0, and suppose if I increase the stress, then there is a linear relation between the stress and strain. So up to some point, this increase of length is very smooth. So whenever you are adding a weight, or whenever you are applying a stress, there is a smooth elongation of the wire, elastic material, to when the length will be increased likewise. Okay, so this will happen up to a certain point of the stress. So at some point of stress, for example, if up to this point may be taken as a, so at this point, this elastic is the system is actually, this is the length, the wire is, the material is actually working or acting with a perfect elastic material. So up to when the stress is reached at this point, then if you keep on increasing the load, that means keep on increasing the load, then the relation between the stress and strain will not be in the linear relation. So up to this, from this point O to A, this Hooke's law is holds good. That means the material will obey the Hooke's law. That means that there is the linear relation between the stress and strain, so that you get a straight line from the O to A. So suppose if when you are stop adding the weight, and you are going to unload the weight from the wire, then there is a compression is going on. The compression is going to happen in the same wire. This compression is again, that means whenever you are removing the weight, the compression will happen. So this compression, that means So the material will regain its original length when you are removing the weight up to this point. Okay. Suppose when you have a weight and if you are keep on increasing the weight, then the relation between the stress and strain is not going to be a linear one. So there is a small there is a quick elongation in the wire. So let's say this as point B. So when you are unloading the stress after this after applying this much of stress, so when of the point B, then this the elastic material, that means the wire is not going to be a elastic anymore, but a permanent elongation will be produced in the material. So this wire will not going to regain its original shape when you are removing the load of this point B. Okay, so this point B is actually mentioned as the yield point. Okay, so whenever you are actually this permanent elongation is happen is actually taken as pointed as a yield point, and now you are actually continuously giving the stress again to the wire. Then what happen is so the extension of the wire is keep on increasing with some friction, so that there is a increase in length with rapidly, and depends upon the time of which we are applying the load. So this extension of the wire goes on increasing, and the area of cross section at the same time. So the length is actually increasing, goes on increasing. At the same time, the area of cross section of the wire will be keep on decreasing. So at some point, maybe let's take it as a point as C. So at this point, the wire is finally will break. So suppose the produced, the given force is actually adequate so that the wire is actually lost its elasticity, the proper elasticity property, and this wire is actually break at some point of load. This is C. So this C is actually taking this load which is actually giving after this up to this point C is taken as a breaking weight. Therefore, when you keep on adding the weight or keep on giving the stress to a elastic material, three different things is happening in the wire. So first, initially for the small strength, small stress, the system, the wire or a material will obey the Hooke's law. That means there is the linear relation between the stress and strain, and after some point A, the system will actually having the permanent elongation. The wire is actually having the permanent elongation up to the point B, so that after, suppose if you are increasing the load, keep on increasing the load, then the area of cross section is actually keep on reducing rapidly, and at the same time the length is also rapidly increasing. So at some point the area of cross section is going to be near zero, so that the wire will break. So this is actually happening when you are actually keep on increasing the stress. So suppose if you are having a wire with some area of cross section, and the length is actually taken as L, and the area of cross section is taken as A, and the force which you are giving is actually F, then the stress is actually given as, you already know that this is the force divided by the area of cross section. So the force which is actually required to break the wire, which can be taken as a F, the critical value, that means F CRIT, F under subscript with the CRIT, that is the critical force in which the wire is actually breaking, the breaking is happening. So that is actually taken as a force, that means the F critic, and divided by A, which is actually mentioned as the breaking stress. So every material having its own breaking stress value. So depending upon the force we are applying, so and the depending upon the property of the material, this is also depending upon the area of cross section of the material. Suppose if you are having the same material with a different area of cross section, then this breaking stress will vary depending upon the area of cross section of the given material with the same material. Also, it is found from some different experiments that even within the elastic limit of the given wire, so practically all the substances, all the materials take some time to reach their original length after the deformation force is removed. So this delay is actually delay of recovering back to original condition, or a removal of reforming force is called the elastic after effect. After effect. So when you are applying a load, and suppose if you are removing the force, the length of the wire or length of the material is actually not actually coming to the original, with deforming. The deformation time is not actually happening instantaneously, but it takes some time. So that whenever you are doing experiments with the elasticity, suppose if you are loading and unloading weight, then then you have to wait for some time to to the material to regain its original length. So that is called the elastic after effect. So suppose if you are doing experiments with the quartz or a silver, gold, these materials having a very low elastic after effect time. So that suppose if you are using this as a suspension wires in different experiments, then this elastic after effect will be very less. That is why the quartz fiber used in many experiments. To suppose if you are using the torsional pendulum or any material, any apparatus, you are mostly using this quartz because it is having a high elastic property. Also, suppose if you are adding a load and removing the load, this quartz is actually having the very low elastic after effect time to regaining its original length. So as I told you that, so suppose if I remove increasing the stress of the wire, then the length is actually increasing. At the same time, the cross section of the area is decreasing. So this is the ratio between the elongation and the lateral strain and longitudinal stress that can be given by the ratio that is called the Poisson's ratio. So this Poisson ratio is also depending upon the material which we are using. For example, different materials having their different Poisson ratios. So the rubber is actually having the high Poisson ratio is the range of 0.5, and the low range, the material which is wood or cork, which is actually having the Poisson ratio of 0. That means whenever you are going to apply a force on the cork, then there is no the elongation, the compression or the elongation is going to happen in the material cork. That is why this cork is actually used as a cap in the glass bottles. So whenever you are applying, when you are going to removing the cork with the enormous stress, then there is no reduction of the cross section, so that the Poisson ratio will be equal to 0, nearly equal to 0. So that is why this cork is actually used in the different glass materials as a cap. So the rubber is instead, on the other hand, the rubber is having the almost equal to the Poisson ratio, which is actually equal to the 0.5. So which is having the high elastic property. So we are going to take this rubber and we are going to find out what is the Poisson ratio, and how to find out the Poisson ratio of the rubber with a small experiment, which we are going to see in this, which we are going to see next. So determination of Poisson ratio of rubber. Okay, so for this finding out the Poisson's ratio of the rubber, we are going to take a rubber tube, which is actually used in our like a cycle tube. We are going to take a other kind of tube. So this tube is actually maybe taken as like this, with some area of cross section, and so you are going to close the rubber tube with the rubber with a rubber cork for the both ends, this end as well as the other end. with the rubber. We are going to close the car, and you are going to inserting a glass tube. This glass tube is actually having the open ends on the both sides. You're going to add the water in it, so that this tube is actually filled with the water, filled with the water, and up to this some threshold value of the up to the glass tube, which is taken as a G. Okay, so so the whole apparatus is actually fixed with the another supporting beam. So the supporting beam is maybe it's taken here like this. Which is that the whole apparatus is fixed with this beam. Okay. So what I'm going to do is I'm going to add a small pan, a scale pan here, a small pan, which is actually I'm going to add the weight here, and this the end of the wire is actually having as a needle or a pin. This beam is the beam is actually having as a scale on it, measurements in the scale, so that the pin is actually using to measure the corresponding length of the tube. So when you are adding a weight, then the rubber will get elongated, so that this pin is actually pointing some measurement in the scale, so that you can easily find out what is the elongation length. And similarly, suppose if you are adding a weight, there is a elongation in the length, and at the same time there is a contraction in the area of cross section. This area of cross section will be taken as a. So this change in cross section can be measured from this the position of this water from this meter scale, so that you can have two different telescopes, one here and another one is here, to measure this telescope 1 and this telescope 2. So you can measure the measurements between the wire's position, between the water position from the telescope 1, and the length of the wire changing in length can be measured with the telescope 2 with the measurement scale. Let's take this point as P. That means we are increasing the value, so that you can easily find out what is the P value just by measuring it using the telescope. Okay. So as I already told you that this glass tube is filled with water, so that suppose if there is a change in the area of cross section, so and there is an increasing in length, then there is a change in the volume of the total volume of the corresponding rubber tube, so that this can be easily found out from using the water level. Okay, fine. So what I'm going to do is, first I'm going to add the some weight, so that this length is actually increased. The length is taken as a L, so the length is actually increased for some value, so that the initially you are actually measuring the point P without load, and when you are adding the load, this area, the length is actually increased. This increase in length can be measured with the telescope, which can be taken as with the change in length can be taken as DL. Okay. Similarly, there is a change in length. At the same time, there is a change in the area of cross section, or a change in volume, so that the change in volume can be taken as dV, and this dl and dv will be measured for the different weights. Suppose you are loading a weight, and you are calculating the measuring the position of the P, and you are kind of point out the change in length. At the same time, measuring the water level in the position G. Maybe it's when you are increasing the length, then the volume will increase, so that the G will actually going, the water level is actually going in the downwards, so that you can easily measure each and every point for the corresponding loads. So the relation between the DL and DB, that is the Poisson ratio, can be measured with calculated with the formula 1/2 times of 1 minus 1 by A, that means area of cross section, and the change in volume divided by the change in area. So this is the formula which we are going to use to find out the Poisson ratio of the rubber. So you already know the area of cross section A, and the dV is actually called dV, and sorry, this is dl, dV by dl. So this dV and dl is actually you are calculating from this experiment, and you are substituting the values, so you can find out the average value of the mu. So what we are going to do is we are going to derive this formula from the we are going to derive this formula here now in the now. So let us consider the length can be mentioned as L, that means the length of the tube, and so for find out the area of cross section, we are going to find out what is the diameter is, which is taken as a D. D is nothing but the diameter of the rubber tube, and the A is the area of cross section, and the V is the volume, total volume of the rubber tube. Okay, so that we can easily find out the volume, which is equal to the area into the area of cross section into the total length of the glass tube, so which will give you the volume. Okay, so when you are doing the experiment and then you are applying a load, there is a change in volume which is actually taken as a dV. There is a change in volume, and similarly, change in volume means there is an increase in the volume, and at the same time the dl, which is actually the change in length, that means the increase in the length, and so that the area of cross section is also vary in the changing, which that means that there is a decrease in the area of cross section, that can be taken as a dA. Okay, so this is change in volume, that means increase in volume, and change in length, again it's increasing when applying a load, and there is a change in area of cross section, that is actually decreasing. Area of cross section, this is actually decreasing. So that I can change this formula as that means the total volume plus the change in volume, which is equal to total area minus decrease in area into the total length plus the increase in length. So I can just multiply this equation as AL minus L into dA plus A into dL minus dA into dL. So here you can see this there is the dA and dL is very small. There is a small change in the length as well as area. So this multiplication will give you the negligible result, so that I am going to omit this dA by dL, means the dA into dL. Without this, I can write the equation V plus dV, which is actually given as like this. Okay. So we already know this this AL, there is nothing but that's actually the volume. Okay, so A into L is nothing but the volume, so that I can write it as V minus L into dA plus A into dL. This is nothing but the V plus dV, so that I can just cancel out this V and this V, so that the finally I can find out the V dV is equal to A into dL minus L into dA. So this is the change in volume. So I can take this as equation 1. So I have a dV is equal to AdL minus L into dA. That is my change in volume. That means the increase in volume. So as I already know this, the value of A, that means the area of cross section, which is taken as pi r squared, and r is, we already have the diameter d, which we already have here, the diameter d, so that r can be written as d by 2. So r is equal to d by 2, that is my radius. So I can just substitute the value, so that I can find out the A is equal to pi d squared divided by 4. I can just substitute this r squared so that I equal the d squared by 4. So that is my the area of cross section. So that I can find out the change in cross section as the dA. So I can just take the derivative of this. So the pi is a constant, and I can take the derivative of this so that I get the 2d into the derivative of the diameter divided by 4. So that I can cancel out this, and finally I can get the value of dA as pi into the diameter into the change in diameter divided by 2. Okay, so this is the dA value. So the dA is equal to pi d, the derivative of the d divided by 2. Okay, so I can find out take the ratio of dA divided by A, which is the rate of change of the cross section. I can write this as pi d, the derivative divided by 2 into the area, which is I already have, which is as pi d squared by 4. I can write this 1 by A. I can write this as 4 divided by pi d squared. So I can just simplify this equation by cancelling out the constants d and small d with the 2, so that the final answer will be equal to 2 times of the derivative of d divided by the original diameter, that is my dA by A. So from this equation I can just multiply this the whole equation with the A. I can get dA, which is equal to 2 times of A d, the derivative of the d divided by d. So that is the change in the area of cross section. So I know the cross section, the change in cross section. I can directly substitute the values in the d in the equation 1, so that I can I can find out what is the change in volume. So dV, which is equal to A dl minus the dA. dA is L into dA. So 2AL divided by d into dd. So that substitutes into the value of dA here, so that I can dA into L. I can write this as here, or I can just again divide this equation by A into dl, this equation, so that I can get dV divided by A dl, which is equal to 1 minus I can just this A and A will get cancelled, and the dl will come here, so that I can write this as 2L divided by d into dd divided by dl. Okay, so this is my after just deriving dividing this whole equation by A into dl, I can get this equation, which I can rearrange as 1 by A times of dV by dl, which is equal to 1 minus 2 into dd, the derivative of the diameter divided by the dl divided by the total length. So here you can see this dd divided by d and dl divided by d, which is nothing, dl is nothing but the lateral strain divided by the longitudinal strain, which is nothing but the Poisson ratio V, so that I can just substitute the V instead of this the term. So I can write this as 1 divided by A dV by dl, which is equal to 1 minus 2 times of V, or I can find out the V from this equation, that is equal to V is equal to 1 by 2 times of 1 minus 1 by A dV by dl. Okay, so this is the final formula where we have used here 1 by V 2 times of 1 minus 1 by A dV by dl. So I can easily calculate the area of cross section is actually constant for the particular rubber the rubber tube which we are taking, and from the experiment I can calculate the change in volume and change in length. and then you can just substituting the values here, you can find out the value of V. So from the experiment, the value is approximately equal to 0.4999. That means almost equal to 0.5. That means the rubber having the Poisson ratio of 0.5, which is having a very high positive Poisson ratio from the known materials. Okay, so this experiment you can do it with a simple. You can do it in the simple lab experiment. You can just filling the water tube with the water, and suppose if you have a sophisticated measurement measure apparatus to measure the length as well as the change in volume. That means that if you have two telescopes with a meter scale, then you can easily find out the change in volume as well as the change in length, and you can calculate the Poisson ratio of the rubber from this simple experiment. Okay. So stop here. So and suppose if you have any clarification, any doubts you have, then you can clarify it in the class. Okay. Thank you.